Hello, I am going to talk about Delaunay triangulation and I am Madhu Prasad. Before going into the topic, we have to know certain definitions, theorems, and lemmas. Uh, First, it is triangulation. What is triangulation? As the name suggests, triangulation is nothing but splitting a polygon into triangles. That is, a polygon can be divided into triangles. This is the basic thing. The definition is as follows: like P is a set of points in the plane, and a maximum planar subdivision is a subdivision such that no edge connecting two vertices can be added to S without destroying its planarity. Like in simple terms, there should not be a edge such that it destroys the planarity of the given graph. So a triangulation is now defined as the maximum planar subdivision whose vertex set is P. So that is a triangulation of P. Next is convex hull. Here convex hull, you just want to know that given input set of points like P1, P2, P3 here, you find set of another points in the given input such that it acts like a boundary to the whole points. To be more precise, it is the intersection of all the convex sets that contain S. That is called a convex hull. Um, Next, it is a theorem. Let P be a set of points in the plane and not all collinear. And K is the number of points that lie on the boundary. That is the thick lines here. This is the convex hull boundary. Such that we derive that any triangulation of P has 2n minus 2 minus k triangles and 3n minus 3 minus k edges. The proof for this theorem is available in the internet. You can check for it. Next is angle optimal triangulation. Let T be a triangulation of P and suppose it has M triangles. Like you have a triangulation and it has M triangles. So totally there must be 3M angles in it. Like every triangle has 3 angles in it. Then A1, A2, A3 up to A3M be the sequencing triangles. We are arranging that sequencing triangles in increasing value. And we call A of t as the angle vector of t. A of t contains all the increased angles, and t dash be another triangulation for the same set such that A of t dash equal to A dash 1 up to A dash 3m. We say that t is larger than angle vector of t dash if and only if at is lexicographically larger than a of t dash. We denote this as a of t is greater than a of t dash. Uh, this is called as angle optimal triangulation. Only a of t is greater than or equal to a of t dash. This is called angle optimal triangulation. Theorem 2, that is Thales theorem. Consider a line L cutting a circle at points A and B such that there are 4 points available: R, P, Q, and S. R lies inside the circle, PQ lies on the circle, S lies outside the circle. So, given this structure, we derive that A of RB, that is the point lies which inside the circle, the angle is greater than the point which lies on the circle, and that is greater than the point lies outside the circle. That is ARB angle is greater than APQ angle, or which is equal to AQB angle, and ASB angle is less than that. This is Thales theorem, and next is edge flip. Edge flip is nothing but consider this convex polygon, that is it is a convex quadrilateral. uh, what we are trying to do is, after a triangulation is being done, this is the existing quadrilateral after a triangulation is done, such that pi and pj is an edge of the triangulation. Since it is a convex quadrilateral, and hence we can flip the edge and have another triangulation, that is Pij. After an edge flip becomes Plk as an edge, and Pij's edge is being destroyed. And why do we need this edge flip? There is a purpose for this. If the minimum angle of this is less than the minimum angle of this, it means that the P of ij is illegal. That we are seeing in the next slide. Checking for an illegal edge. Uh, Assume that Pij is an edge after the triangulation, and pk is an inserted point. If we consider a circle having all the points pi, pk and pj in it, if there exists another point pl inside the circle, it means that the edge ij is illegal. This is the actual thing of checking an illegal edge. This is how you check an illegal edge. This is said by this is like proved by lemma 9.4. This is the algorithm for it. Like input is some triangulation of function p, and output is a legal triangulation. We have already seen what a legal triangulation is. While tau contains illegal edge pij, if we find that pij is illegal, how do we find that? Like with that lemma, do flip, that is pij is being flipped, let pijk pijl be two triangles adjacent to pij, and remove the pij from town, add pkpl instead. That is like we are removing pij and we are adding pkl, such that if we draw a triangle with pj, pl and pk, pi may lie outside. That is not the purpose of it, but finding the illegal edge and flipping the edge is the this algorithm's job. Next is Voronoi diagrams. Let P be a set of endpoints on the circle. P be a set of points, and uh, Voronoi diagram is the subdivision of the plane into n regions. That is, all the points are uh, divided into certain regions. All the points are allocated with certain regions, such that the region of a site P contains all the points in the plane for which P is the closest site. As this is a site P, the region which it contains, that is this quadrilateral. Sorry, not a quadrilateral. This is this polygon. In, every point in this polygon is nearest to this point. So that is what a Voronoi diagram is. This is like a formal definition and all the notations for Voronoi diagram. A region of a site P is called a Voronoi cell. That is, this is a Voronoi cell. All the dots in it and all the areas which are covered is called the dotted lines is the Voronoi. They are denoted as bu or bar of P. They are nothing but the region corresponding to the point. So this is a Delaunay graph. That is, after this being done, this is just Voronoi diagram. We can easily obtain a a Delaunay graph. That is how these two are related. Uh, Consider each points side points here, and the each point is associated with a face. That is, this is a face, and the point is sharing face with other faces. That is this this and this. Each side is sharing an edge with other, so such that that point is connecting an edge to another points, that is vertexes, sorry, other vertices. So uh, I think you get it. The point is this. Assume that this is the point we are discussing. Uh, the dotted lines are the faces, or the edges, that is making up the face of this point. So this region is sharing edges with other regions. So the point in the region which shares with other regions connect the edges, like this point connects to this. So it means that they all share a common edge between their regions. This is what a Delaunay graph is drawn. Actually, this makes sense with the thing now I said. And instead of curves, if we do straight lines, it becomes a Delaunay graph. That is it. Next is theorem 3. Delaunay graph of a planar set point set is a plane graph. This is a theorem you want to know. and you can see for proof in the internet or any books. If this is an information which you need to know, if a vertex set of Voronoi of P is a vertex set of the cells, that is this the dotted line is nothing but the Voronoi regions. If you consider an vertex in the region, that is all these things are the vertices. Uh, if you consider a vertex in the Voronoi region, this F is the face made by a Delaunay graph. If we consider that the vertex crosses all the edges of this Delaunay graph, it means that all the edges are in a circle with V as its center. This actually does not happen often. That is 4 points in a circle. We always have 3 points in a circle, at most 3 points in a circle. This is for an example purpose. The information is that in the situation the points P1, P2, P3 up to Pk, these points, these are assumed to be P1 to Pk around a circle around V. So we not only know that F is like K-gun, that is polygon. But we even know that it is convex. Yeah, it is obviously going to be convex, which lies on the circle, since it lies on the circle. Next is, if the points of P are distributed at random, the chance that 4 points happen to lie on the circle is very small. So that is what I said now. If 4 points lie on a circle, it is not a general position. If sorry, I think I said it wrong. A set of points in general position if it contains no 4 points, that is, if does not contain 4 points on a circle, it is called general position. If P is in general position, then all the vertices of the Voronoi diagram have degree 3. So it is the only reason we have triangles. This is why we call Delaunay triangulation. Actually, triangulation means that that is this is the definition, which means actual triangulation. We define a Delaunay triangulation to be any triangulation obtained by adding edges to the Delaunay graph. If we add edge to the Delaunay graph, it is called Delaunay triangulation. That is adding an extra point and adding edges. We'll see that soon. This is another theorem. This theorem states that this theorem is actually was it is equivalent to Voronoi diagrams, which is like slightly altered so that it can be applicable to the Delaunay graph. This theorem states that Pijk or belongs to P are if the 3 points or vertices of the same face of a Delaunay graph. These 3 points are called vertices of a Delaunay graph only if the circle through the 3 points contains no point in its interior. This is what called a vertices of a Delaunay graph. 2 points are called an edge of the Delaunay graph. One, if and only if it contains one, if and only if P and I and J, PA and PJ are in the boundary of a closed disk and does not contain any other point of it. So these are the this is a theorem on Delaunay graph. And theorem 5, let P be a set of points. The red thing is the theorem and this is the interpretations from the theorem. Let P be a set of points in the plane and triangulation T of a P is legal if and only if T is a Delaunay triangulation. That is, what they are trying to say is that a triangulation is said to be legal, any triangulations is said to be legal if and only if it is a Delaunay triangulation. There are other triangulations other than Delaunay triangulation. So another thing we want to know is that since any angle optimal triangulation must be legal, that is, theorem 5 implies that this is what implies those Delaunay triangulations or angle optimal triangulations. So since any Delaunay angle optimal triangulation must be legal, so it means that any angle optimal triangulation of P is a Delaunay triangulation. This is just obvious. When P is in general position, that is there is 3 points, there is only one legal triangulation, which is then only angle optimal triangulation is the Delaunay triangulation. If P is not in general position, then any triangulation of Delaunay graph is legal. How they are trying to say is that their angle vectors do not differ too much. So what they are trying to say is, if P is not in general position, that is if they are not triangles, any triangulation of the any triangulation other than Delaunay triangulation of a Delaunay graph is legal. It means that any triangulation is equivalent to Delaunay triangulation. How they are doing it is they are comparing the angle vectors, so it doesn't differ too much. Moreover, using Thales theorem, one can show that the minimum angle in triangulation of a set of co-circular points is the same. That is, minimum angle is independent of the triangulation. What they are trying to say is that uh, um, the minimum angle is independent of the triangulation. That is, according to Thales theorem, that is, by comparing the angles, we can say that any triangulation can be Delaunay triangulation. That this is not an important topic, but you can know theorem 6. Let P be a set of points in the plane. Any angle optimal triangulation of P is a Delaunay triangulation of P. Furthermore, the Delaunay triangulation of P maximizes the minimum angle over all triangulations. This is just using the before theorems interpretations. We are proving another theorem. Uh, this is the important part. Computing the Delaunay triangulation, the algorithm. That is, it is easy to compute Delaunay triangulation using Voronoi diagrams. By first drawing Voronoi diagrams, we can easily compute the Delaunay triangulation. But actually, we are not doing that. We are doing a direct method. This initially we are having P0, that is P0 is the topmost point, that is the highest point in the given graph. This is the given point, sorry, this is the given points. P1 and P2 are 2 points which we are taking such that together with the highest point P0, P forms a triangle with P0, P1 and P2. To avoid problems caused by unbounded regions, we are drawing this big triangle to avoid the problems caused by the unbounded regions. This means that we are computing Delaunay triangulation with these two extra points. Later, if we want, after all the algorithms is applied, we remove the edges from these 2 points, and what we result is in the original triangulation of P. This is enough in this. Next is that if the given a triangulation, that is you will be given with the initial triangulation, we will be adding points in the triangulations such that that point can lie either on inside a triangle or on the edge of a triangle. So if it is inside the triangle, this is the case. We will be splitting the triangle into three triangles. That is, if PR is inserted into the triangle PIJK, it will be split into these three triangles. If suppose the PR is on the edge of a triangle, the two triangles sharing the edge has to be split into four triangles. That is like this. This is simple. I'm going to the next thing. Algorithms. The main algorithm. The input is set of points in a plane. That is, give a set of points. That's it. Like stars in the sky. Output is a Delaunay triangulation of P. Next is let P be a lexicographically highest point. That is those thing we saw P0. We are finding the P0. P1, P2. We are assuming points are sufficiently far away from the other points so that they don't disturb the Delaunay triangulation of the side points. Sorry, the original points. And we are drawing the triangle P0, P1, and P2. We are initializing tau as a triangulation consisting of single triangle. That is the thing just now we said. We are then now starting for 1 to n, that is for all the points. We are finding a triangle PIJK containing PR. That is, after adding the point PR, we are finding the triangle which contains PR. That how would you find the triangle? We are going to see in the next slides. If P, like that is, we are seeing the next slide. That is, if PR lies in the interior of the triangle, that is the first case we saw just now. If it lies inside the triangle, we are splitting the triangle into three triangles. So after splitting the triangle into three triangles, we have to check all the edges to be legal or not. That is done by legalization. This is nothing but similar algorithm which we saw before, like the legalized legal triangulation algorithm we saw before, proving using that lemma. We are splitting the after the triangle being split into three triangles, we are checking each edge Pij, Pjk, Pki to be uh, uh, to be legal or not. It is obvious that only the edges which are changed after the addition of point is going to be legal. The only possibility is that after the addition, what the edges which are related to the addition of point are only going to be illegal. So we are only checking the Pij, Pjk and Pki. That is the three edges which are going to be affected after the addition of points. Okay, this is about the PR. That is, we will shortly see what legalized edge function is all about. And suppose if the point lies on the edge of a triangle, we are splitting the triangle into four triangles. So it is going to be four legalized edge functions calling the four related edges. And after the loop is over, we will get a triangulation which is Delaunay triangulation, which is an angle optimal triangulation. After that, we are discarding P1 and P2 with all their incident edges from the original points. So next we are returning to legalization function. This is the legalization algorithm. If Pij is illegal, that is, if you find an algorithm illegal, how do you find an algorithm? An edge is illegal. Using that lemma we saw before. Then let Pi Pj Pk be the triangle adjacent to Pr Pi Pj along with Pi Pj. That is, you are finding the edge which is illegal. You are flipping that illegal edge. So now again you are recursively calling the next edge which may be illegal. So in this algorithm like searches recursively up for all the edges which are going to be affected by the edge. You can see this here. uh, there is a single point PR in this region. These gray regions are the triangles which are going to be affected. So after the triangulation, after the legalization, we find that all the affected triangles are supposed to meet on the PR point. They are going to be connected. That is, they are going to be incident on PR. This is what legal triangulation does. Okay, this is actually the algorithm. You can read the PPT if you want to be more confident in the topic. The thing is, now the problem is how to find the point how to find the triangle containing the point. That is which I said before in the line 7 of the algorithm. uh, Now first, while we build the triangulation, we also build a data structure. That is, the data structure is a directed acyclic graph. The leaves of D corresponds to the triangles of the current triangulation. All the leaf nodes, thus, these correspond to the triangles of the current triangulation, and we maintain cross pointers between these leaves and triangulation like this. The internal nodes correspond to triangles that were in the triangulation at some earlier stage. That is, as the triangle grows, the internal nodes corresponds to the stages in the process. Uh, I can explain it the picture easily. Assume that these are the triangles in the initial triangulation. There is a point PR added here in triangle 1. So there are three triangles with the root node as that are as root node. That is the biggest triangle P0, P1, P2 is having three triangles delta 1, delta 2, delta 3. After the adding triangle in delta, after adding a point in delta 1, it becomes like this. We divide the triangle into three triangles. That is, triangle 1 delta 1 has three triangles. Now delta 2 delta 3 remains the same. After flipping the edge, that is legalizing the edge, we find that delta 1, that is this triangle, to be converted into delta 4. That is delta 2 is converted into delta 4 and delta 5. That is delta 2, this is converted into delta 4 and delta 5 after Pi and Pk as the flipped edge. Again we are finding for the illegal edge, and we find that delta 5 is split into delta 6 and delta 7. So delta 3 is not being altered, now combines with delta 5, convert it into delta 6 and delta 7. You can understand this if you take a pass and look at all the images. Now next thing, the biggest thing is sorry, it's a simple thing, how to choose p1 and p2. You cannot choose p1 and p2 randomly. It should be chosen such that it does not affect the order of the that is, it does not affect the Delaunay triangulation of the original points. So we are choosing P1 and P2 such that they're they're sufficiently far enough from the points. So this is all about Delaunay triangulation. Some applications are and terrain modeling is also a main application of Delaunay triangulation. Thank you.